So there are many ways to do that. One way to do that is, I'm going to explain one, sorry. One way to do that is, let's take a small square. We don't know what is the square and how to measure a square. And we'll just make sure this square is inside that circle. Okay. And how can we make sure that inside the circle, it is inside the circle? All you have to do, just measure this distances. Measure these distances of all the vertices of the square from the center, and make sure these distances is less than 1. If you just do that, then that is good enough. Then we will know that that square is inside the circle. Okay. Then what I did, I choose age equal to exactly 0.2. So if it is 0.2, then what is the square? The area of the square? 0.2 square, right? So that will be 0.04. Correct? Are you with me?
Yes.
Yes, sir.
All right, just a minute, one thing. So 0.04. Now question is, how many such square we can fit into, maximum how many such square we can fit into this circle. So I try to fit as many as square possible, and turns out, if you can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So half of is 26 and rest half is 26. So 26, 26, 52. So there are 52 such square. So each square is 0.2 square is 0.04, and 52 such square is there. Sorry. 52 such square is there. 52 into 0.04 is how much? 52, let me just calculate it. Is 2.08. 2.08. So the value of pi from here, we can say, is definitely this total area. If we say the area covered by this geometric shape, right? This entire geometric shape is 2.08, correct? Let's call this entire geometric shape as A52. This entire geometric shape, the area is 2.08. And this geometric shape, the area of this geometric shape must be less than the area of the pi, which is A, which is, I mean, the area, if we call it, which is actually pi. Sorry. Let us use a slightly different notation, okay? Otherwise, I'll just make it. So let's, sorry. I'm messing up with the notation. Let's not mess up the notation. So this geometric shape I'm calling A52 because I'm just denoting this geometric shape, and the measure, the area of A52 is 2.08. Okay, are you guys with me? And
Yes.
the entire area is this circle, I'm calling it A, and mu of A is pi. So the area of the circle A is pi, and mu of 52 is A52, this geometric shape, whatever that geometric shape, weird geometric shape is coming up, is 2.08. So that must be less than mu of A, which is pi. So the value of pi must be greater than 2.08. Okay. Now what I have done, I am reduced the h from 0.2 to 0.1. And turns out now there are 268 squares. I did the program and I counted it. It's manually, it's not possible. It's very difficult. You can. And that raise up to a new geometric shape. This entire thing, let me use a different color. This entire thing is a new geometric shape. This entire geometric shape is, I'm calling it as A268. A268. Okay. And what is the area of this geometric shape?
2.68.
Um, 2.68
268 into 0.1 square.
correct. So 0.01 square times how many? 268. So that will
So
come.
0.1 square.
Sorry. Yeah. 0.1 square is, sorry about that. Yeah, 0.1 square into 2.68, that makes it 2.68. Now clearly the area of 268 which is 2.68 is definitely less than the area of circle, because the entire area is inside the circle. So that means pi, the value of pi is definitely greater than 2.68. Now you understand where am I going. Now I have reduced it to 0.05. I did the calculation, exact same thing, 0.05 square. Turns out there are 1168 such square you can inscribe inside the circle. And that gives you a new geometric shape, complete new geometric shape. And the area of that new geometric shape turns out to be 2.92. Again, that area is less than pi, because that area, no matter what, that area is definitely less than the area of the circle. We can see there are areas which are not covered by this geometric shape, like this area, this area. These are all open areas, right? That are not covered by the of the geometric shape that we are interested in. So, and then I push it to boundary 0.04, that goes to 2.95. I push the boundary to 0.03, and that makes it 3.02, the area. I did the same calculation, 3.02 turns out. And then I push it to 0.02, and turns out there are 7,628 such square you can inscribe in the side circle. But technically you can still see there are areas which are not covered. Correct? So these are the areas you can see, there are areas which are not covered. Correct? So that means these geometric shape, which is almost like a circle but not circle, not a really smooth circle, still jittery, the area of that will be still less than the area of the circle. So that means that area is 3.05. So that means value of pi is still greater than 3.05. Well, let's see what happens. I push it to 3.01. I mean h to be 0. H equal to 0.01. When I push h to 0.01, there are 31,000 small squares that can be inscribed inside the circle. And that resulted the area to be 3.1. But we do know still there are in the age, conceptually we can think like that, okay, there will be still some area which will not be covered by this geometric shape. That geometric shape is almost circle, but it is not yet circle. So definitely pi is greater than 3.1. Okay. So pi is greater than 3.1. That part we do know, but can we say that what is then pi? We know one can come and say, well, pi might be 3.5. How do you know? It's not 3.5. So that means we got a lower bound for the pi, but can we get an upper bound for the pi? So now we take another approach. This time the approach is we will take the squares, and as long as one of the vertices is inside the circle, I will take it. So previously what was my strategy? Go back. Let's go back. Here my strategy was all 4 vertices of the square has to be inside the circle. If you do that, you will always end up this kind of scenario. Now I am taking a completely different scenario. Now I'm saying that as long as instead of all 4 vertices, as long as one vertex is inside the circle, I'm good. Sorry. Yeah, this is the one. This is the one. Yeah. So I took h equal to 0.8, 0.2, h equal to 0.2, and I said as long as one vertex is inside, I mean from the center, I'll take that circle. So that means this circle, you can see this circle partly inside this square is partly inside the circle and partly outside the circle. Similarly, if you consider this square, as long as I said the one is out inside the circle, one vertex is inside the circle, I'll take it. So partly it is inside the circle, but there is a part which is outside the circle. Correct? So this is the part which is outside the circle, and this is the part which is inside the circle. So question is, what is the area of this new geometric shape? The area of this, there are 88 such circles, what we figured out. And turns out the area of this new geometric shape is 3.52. And this 3.52 must be the area of this geometric shape, mu, I'm calling it B, 88, this geometric shape. The area of this geometric shape must be greater than the area of the circle, which is pi. Okay. Now, I took the same strategy. Now I reduce the age to 0.1. Now I got 344 such circle. Now this 300 and B 344 is a set which is a subset of B of 52. Can I say that? Because this geometric shape will be some sort of, smaller than this geometric shape. And that will inscribe the entire circle A. And as a result, I can say the measure of B344 is 3.44, which is definitely less than the area of the circle, which is pi. Now we are starting to develop an upper bound for pi. Now I push h to 0.05. Now that gives me 1326 squares, which completely inscribed the circle. And this B1326 is definitely a subset of B344. And A is a subset of B1326. So the area of B1326, in some sense, will be 3.315. Do the same calculation, and definitely that is greater than pi. All right, let's push the boundary. What about taking h 0.04? Now it is same logic going on, 3.267. I push h equal to 0.03. Now it is 3.229. The area is 3.229. So it is like going from the outside is going in kind of thing. It's shrinking. The previously it was expanding from the inside and it was making almost a circle. And now when we started, it was like outside, from the outside, it is shrinking inside. And that turns out to be 3.211 when you are taking h equal to 0.02. And finally, when I'm taking h equal to 0.01, it turns out that we have 31,796 such square which completely inscribed the circle, which is still superset of the circle. Circle is completely inside this geometric shape. This, whatever the geometric shape is, it's conceptually, we can just think about it. We don't know. Almost like a circle, but it's not circle. Circle is this guy, A. And the area of this geometric shape is 3.18, which is still greater than pi, the area of the circle. So now we have a bound. And what is that bound? That pi is definitely less than 3.18 and greater than 3.1, right? That is what we found, correct? But we can push the limit, then we do know what happens. And if you keep computing this an and bn as h tends to 0, eventually it will come out something like that. And what kind of limit that we are actually computing? The limit that we are computing for the one which is going from small to big, we are taking, so what you have, say, when we are, what are the geometric shapes that we have to begin with? Let's, sorry about that. Oops, sorry. So it's like A52, then A268, this way, right? These are all the geometric shape that we have. Now in this geometric shape like A1, sorry, I don't know why. A1, A2, A3. Now we do know this A1 is superset of A2 and A2 is, sorry, subset of A3. So because it's growing, right? So it's going AN. Now I don't need to check for the all. What I will do, I'll just say that, okay, give me I can compute the mu of A1. I can compute the mu of A2. I can compute the mu of A3, the basically area, and I can compute the mu of AN. Then I'm saying, give me the largest of all of them, whatever be the thing that is supremum of that is supremum of all this mu of AN. And that actually that is the largest of all the mu of AN. That guy is going to converge to something. Where it is going to converge to mu of A. And same concept I am doing here also. So when I'm looking for Bn, the area which are going from outside and coming, shrinking to the circle, what I am doing? What am I doing? I'm just taking B1, which is bigger than B2, sort of a superset of B2, which is a superset of B3. And I keep doing. There is a Bn, and which is a superset of A. So I do know mu B1, the measure that I'm doing is some sort of a greater than mu B2 in this way, and it is finally mu greater than A. So what I don't want to keep track of everything. I just said, I'm not worried about everybody. I'm just worried about the smallest of the infimum of mu Bn. Smallest of the mu Bn, because the way the Bn is being constructed, mu of Bn will be always greater than mu of A. The way Bn is constructed, the area of Bn will be always greater than the area of the circle, no matter what. So all I'm asking that I'll just look for the lowest of the Bn area, and if that guy is going to converge with the mu of A. And that is what it is exactly happening. And that is where the limit from the above and limit from the below, that concept is coming up. Okay, guys. Now, in order to compute this, we needed a computer. I needed a computer, but Ramanujan's came with this formula. And I have no idea how, and don't ask me, how he came up with this formula. Remember that he didn't had any computer in this. 100 years back, there were no computer. So forget about it. So he had to come up with a really beautiful formula using which he can compute the value of pi. And he computed many other formulas for phi, but this is one of the very useful formula. But there is, if you look at this formula for a while, you will find there is a conceptual connection with what we just did and what Ramanujan's formula is. Can you tell me what is that conceptual connection?
Limit to infinity.
Limit to infinity. And there is one more thing. So what he is trying here is saying that, all right, it's like I cannot compute the entire thing. What I will do, I will calculate piece by piece. Is what this formula is telling us, that we will calculate it piece by piece. Like you can think of this, each of them as a of n, then you compute a of 0, then you can compute a of 1, then you compute a of 2, and then keep adding them. And eventually this guy, this entire thing will go to converge to pi. That is where the idea of sequence comes in. Okay. So even in our cases, though we were calculating the areas, but it is sort of a sequence, right? The sequence of numbers, the sequence of sets that we were trying to calculate. All right. Any questions so far, guys? This is a discussion time. If not, then we will do few problem solving. Today is 30th September. All right. All right. So the first problem that we would like to solve, maybe you guys can tell me how can we solve it. square by n plus 1 minus n square plus 3 by n. How can we approach it? Any idea?
We have to find the limit of the sequence.
Correct. Can we find the limit of the sequence?
It's divergent.
Hmm?
Divergent.
You think it is divergent?
Yes.
Can you please prove it?
So we'll find out the limit using calculus and we'll see it goes to infinity.
Okay. What do you think? Why you think it is divergent? Any idea? Because on the numerator you see squares and the denominator you see n, right?
Sir, I think it's convergent at minus.
Okay, how?
Sir, it converges to -1.
Yes, sir. If we take LCM, then the power in the denominator and numerator will be same. That is n square.
So you can write it in this way. I'm just simplifying it, okay? Now, there is one small trick that I'm going to use. That I'll subtract -1 by n plus 1 and add 1 by 1 n plus 1. Now what will happen is I can essentially club this n square by n plus 1 minus 1 by n plus 1 in one side, and I keep, now this guy I can cancel, so this is minus n, this is plus 3 by n, and this will be plus 1 by n plus 1. So now if I just solve this part, then what happens? We can write it as n square minus 1 by n plus 1
N minus 1.
minus n plus 3 by n. I'm writing every steps, I'm not jumping, okay? Then it is n minus 1 by n plus 1 divided by n plus 1. So this cancels. This is 3 by n plus 1 by n plus 1. Correct? So now here I have n minus 1, here is minus n. So this n and this n cancel. So I left with minus 1 plus 3 by n plus 1 by n plus 1. So as n tends to infinity, this guy goes to 0. This guy goes to 0. As n tends to infinity. Therefore, n goes to -1 minus n tends to infinity. So I'll just take a pause here. Okay. What is the, I mean, one thing, I think I also made the mistakes, these things when I was in college, but I think over the years, one thing I have learned, when you are seeing a problem, don't jump into the conclusion, just seeing the numbers. It is better you kind of simplify the problem. So up to this, I think you can always simplify immediately. This trick is bit of a, you need a little bit of practice to develop, to understand that when and where this kind of trick will use. And why I did this trick is, use this trick, I mean, this is not the only way, because if you look into here, if you don't, at this step, if you cancel this, I mean, it's telling you this is minus and this is 3 by n. So I'm not worried about this part. I'm worried about this part maybe. So my hope is if this part get cancels, or or it will stay there. That is my big question, because if it is minus n, then it might lead to a divergence. But if it get cancels, then it might get the convergence. But whether it will be divergent, because it is so simple, a minus n cannot be a simple any farther. But whether it will be convergent or divergent, this guy. So this is now will depend on how your this term is going to simplify. The entire thing at this stage, the whole thing comes down here, boils down at this stage, because I know for sure this guy is going 0, no problem. This guy is just n. Now, if this guy goes to 0, but this guy still n, it doesn't cancels out, then the whole thing will be divergent. But if this guy cancels out and this guy still, goes to 0, then it could be convergent. So the whole thing comes down to how this term will be, how it will be simplified. Although at all it can be simplified. So I saw that, okay, there is an n plus 1. Maybe I do something, and that helps me. So that is where this trick comes in. Okay, so it requires a little bit of practice, but I'm sure you guys will figure it out. All right. At the last week, there was one problem that we kind of discussed and then we have not solved. So that, can we discuss that problem? The last problem was that we have sort of discussed, but we have not solved. Oh, sorry. That find the limit x tends to 0 f of x, where f of x is x and 0 if x is a rational number, and 0 if x is in set of irrational number. So, and when we discuss that how the function will look like, eventually we figure out that okay, it will look like something like this, that for the irrational number, it will take the values like this. On the x-axis, it's always 0. But for the rational number, it will take the values like this. So does the limit exist? How we figure out whether the limit exists or not? One thing for sure, that function is not continuous. Function has infinitely many discontinuity. But does the limit exist?
Well, is even function not continuous at 0?
Okay, so Avishek is saying it's going to 0 anyway. Yeah. All right. So yeah, intuitively it looks like limit is going to be 0. But how we argue that? How we argue that yes, there will be limit, but even if the function is discontinuous, it has infinitely many discontinuity, but still limit exists and it is at 0. But how can we argue that? I mean, intuitively we can feel like looking at the thing. How can we argue that?
Close to 0 doesn't matter either it's irrational or rational. The value is going to be 0.
If we take a rational sequence that is converging to 0, then f of xn is also converging to 0. And similarly, if we take an irrational sequence yn which is converging to 0, we also see that f of yn will be 0 for every term. So that is also converging to 0. So for every real sequence converging to 0, f of xn goes to 0.
Correct. So this is essentially, there are two kind of numbers. One is an, I can say that an equal to n if n is a sort of a irrational number. So it's creating a sequence of numbers, right? And then there is another set of thing which is 0 if n is. So the main idea was here to get the sense of the sequence of numbers, right? And as the things going to 0, then it will go to 0. And another way of thinking about it is also is something like that. So f of x minus, what is the definition of limit? So essentially we want to say that, okay, x, typically how we write? Typically we write that, okay, x is going to some number a, then fx is going to some limit number L, right? And essentially, what does it mean? It means x minus a, if this guy is very small, it's epsilon, less than some epsilon, you can effectively say, if this guy is, you can effectively say that f of x minus L is less than some delta. Correct? this is the idea of, and of course, and then if this is the idea of limit, then in this case, in this particular problem, what we are looking for? Looking for x going to 0, f of x, is it going to be 0? Because for each irrational number, it is 0 for sure. For rational number also, all the, so definitely this is less than epsilon, and then mod of f of x is also less than delta. I can say that for all x which are in Q in irrational number, correct? Sorry. So therefore limit definitely exists at 0. Limit f of x exists. So this is first thing, limit does exist. Limit of f of x exists. And second thing is f of x limit is 0. However, the f of x is I don't know why, how to make it strong. There's something I should. F of x has infinitely many discontinuity. Correct? All right.
But sir, function is continuous at 0, right?
It is continuous at 0. Yes. This is, yeah, this is the fourth point. Fx is continuous at 0. X is continuous at 0. So at 0 it is continuous. Everywhere else it is discontinuous. It limit at 0 does exist. So this is, there are a lot of contradiction, but it's still a very fine, interesting problem. All right.
And also, sir, limit of fx exist at 0 could be better, I guess.
Yeah, that's true.
Excuse me, sir.
Mm-hmm.
I exactly could not understand how we argued this point, how limit existed at 0.
Okay. So if you look into this argument, what is it saying? This is basically the depth. I mean, if you go back to the definition of limit, you take any textbook of the limit textbook and you can find the pretty much this is the definition. What does it mean? It's basically saying, if you go back, let us go back to this. It's basically saying that at 0, if you take a bound on the x, for all the boundary, all the points that are inside the boundary, then you will find there is a boundary here also on the y-axis. All the points are inside this box. And now, as x goes to 0, that means, so suppose first or epsilon become a smaller and smaller and smaller. So that means basically you have first a bigger box, then you have a smaller box, then you have smaller box, then you have a smaller box. As the epsilon becomes smaller, 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 your box is becoming smaller, 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 smaller. And no matter what, whether it's a rational or irrational number, your x and f of x will be always inside that box. Okay? And eventually, it will converge to 0. So whether x is rational or irrational at 0, f of x is 0. So hence there is a limit, and that limit is 0. And at x, it is continuous. But as soon as you're going out of 0, however small might be 0.00000001, the function is not continuous anymore. It will always a discontinuous behavior. Does that make sense? So we have defined the function like that. It's not I have defined, it is a standard problem. It's an interesting problem to
No,
figure
sir,
out.
he replied towards Srijit message just before him.
Is it continuous at k if all irrational values are set to k? Okay, so you want something. I don't get your question. What is the question? Is it continuous?
Sir, he means that like here x is equal to 0 when x is irrational. The function gives 0 when x is irrational. So we get continuity at 0. So if instead of 0, if we define that fx gives k for every irrational, then do we get a continuity at k?
I don't think so. In this case, how can we get a continuity at k? I'm not sure.
In the similar way as we do in this problem.
How do you define, then what will be the function in that case? What is the function f? So if you say f of, wait a minute, if you, I'm not sure what is, I have understood your question. If you are saying f of x equal to k, is that what you are saying?
No, write the previous function, just replace 0 by k.
So
fx is equal to k if x is irrational, and fx equal to x if x is rational.
If x equal to x, if x is rational, and k if x is irrational. Okay, fine. Yeah, you can say that. And then x going to k f of x. Yeah, you can say, then you can construct the function that way. Yeah.
So if we define function fx is equal to 1 by b if x is rational, that is if x is of the form a by b.
What? F of x is equal to
1 by b.
Okay.
If x is equal to a by b, that is x is rational.
X equal to
a by b.
Okay.
That is since every rational number can be written in the form of a by b, that we take 1 by b of that expression, and 0 if x is irrational.
Yeah, I mean, this is a generalized, you are just generalizing the function basically. Yeah, that's perfectly fine. Yeah, that's good. You are thinking to generalize this function.
Is this function continuous at x equal to 0 then?
Probably not. I have to check it out. Probably not, because at 1 by 0 it is undefined, right? In this case, it will be undefined. So we have to be very careful. How are you defining your function?
So at 0 it is 1 because a by b. At 0 we write
I
0.
don't know. I don't know. We can't. I have to check it out. Okay. I have to check it out. I have to think about it. I just can't say whether it is true or not. Okay. All right. What time is it? It's almost end of the session. Look, I was thinking I'll do one more question. Do you guys have another class after this?
No, sir.
Can we do one more problem?
Yes.
Yes, sir.
Let's do one more problem and then we'll go. So, let's look for this. So if I just give you 3 to the power n plus minus 2 to the power n divided by 3 to the power n plus 1 plus minus 2 to the power n plus 1. How will you approach this? And I want to check whether it is a convergent and divergent first. And then if divergent, then we are done. If it is convergent, then can we find the limit? So first question is essentially convergent or divergent. And then second question is if convergent, if divergent, then ends. If convergent, then what is the limit? How do you approach it?
So we divide the whole equation by 3 by n, numerator and denominator both. 3 power n.
3 power n, that will make 1 plus minus 2 by 3 to the power n on the numerator, and then in denominator it will be 3 plus minus 2 to the
Minus 2
plus
minus 2 by 3 power n into minus 2.
right.
And minus 2 by 3 power n goes to 0 for both. So
Okay, let us try that. So you guys are saying divide this entire thing by 3 power n, right?
yes.
So if I do that on the numerator, it will be minus 2 by 3 whole to the power n, and the denominator, it will be 3, and then it is minus 2 to the power n plus 1 by 3 power n, right? Then what you do?
Minus 2 by 3 power n, and in the denominator, both the terms will converge to 0.
What?
We take the limit, then minus 2 by 3 power n will go to 0. And similarly, minus 2 by power n plus 1 upon 3 power n will also converge to 0.
Okay. So the idea is what you are saying, that since essentially 2 by 3 is a fraction, so minus 2 by 3 power n goes to 0, and
So in the denominator, it's better if we write minus 2 by 3 power n into minus 2.
power n into
Minus 2.
2, and this will also goes to 0. So minus 2, this entire thing will go to 0, and this is 1 by 3. This will the whole entire thing. So basically, this entire thing will go to 1 by 3. Okay. All of you understood? Anybody have any doubt?
No, sir.
Okay. There is another way also. I was thinking slightly different way to approach it. So what I was thinking, this is also fine, but I was thinking just check it out if it is a monotonically increasing or decreasing function. So check it out if an plus 1 by an is less than 1 or greater than 1. So if it is less than 1, then what will happen? I can say an is convergent, right? And if it is greater than 1, I can say that it is divergent. And then, so that's how first check whether it is a convergent or divergent, and then you find the limit. So you told me the limit, but you don't told me the whether it's a convergent and divergent. Of course, if the limit exists, then definitely it is convergent. So if first, that is okay also. That's fine. All right, guys. I think it was good discussion. Anybody have any questions or comments or any else to discuss? All right.
Hello. Hello.
Yeah.
Yeah. Sir, I had this question like these kinds of problems are we supposed to expect these kind of problems in the quizzes and the exams? Like, would this be the major chunk, or like will we have any theoretical part? Like some, I think yesterday Kavita ma'am did some sort of theoretical, like using that epsilon prove that some limit or something. So
correct.
It was sort of theoretical, but not exactly like which would be the.
So it will be mix of theory and problem solving. Okay.
Okay.
Because we don't want to do it complete problem solving, because if we just do problem solving session, then problem will be you will develop you will not develop the real foundation of the of the mathematical intuition what resulted it. Like the way you solve the last problem, it's a more like that approach is more like solving problem in the exam. I'm perfectly fine, but as a mathematician, do I like it? The answer is no, because that is not a foolproof way of solving the problem. Foolproof way of solving the problem is you first converge, first you check whether it's a converge or diverge. Okay. And then you go for that's the more rational way of approach the mathematics. And we want to learn mathematics here. Okay. So we want to be little bit of, so you may have to little bit of unlearn some of the things that you have picked up to just crack the exam. So we would like to give you that kind of flavor that, given a problem, how you solve a problem. solve a problem more like a mathematician's point of view. Then we want to tell you in the statistics class, I want to solve you like, okay, one way of doing it is just do some trick, do some problem, and you solve the problem more like a math. But uh, so it will be mix of theory and problem solving. Okay.
Yeah. Is there any specific book that has, like, let's say, these concise? Because the syllabus that the books that were prescribed,
It's
I
big.
mean, they are quite big, like 700 pages. Not something which can be done in a few
I'll
days.
speak to Kavita and try to get back to you.
Okay.
I think Professor Karendikar has a nice book. I'll tell you. I think I have that book. Just a minute. Somewhere, I think I have that book. I don't know whether it's in my.
It's R.D. Sharma, like.
Yeah.
Okay,
That's a
then
pretty cool book actually. It does not have many problems, right? But it has the concept. It's reading that book is very nice experience. I think so. I'll share that book thing with you. I think it is there in somewhere in the syllabus also. Sir Rajiva Karandikar, and who was the other author? Sharma, R.D. Sharma, I think. Yeah. So I'll share that book, detail of that book, and that's a very good book. I think you should have a look into that. That book is not like very theoretically heavy. That is also does not have a lot of problems to solve. But if you read through that book, I'm pretty sure you will develop a lot of mathematical intuition. So reading that book will be a very good experience for you.
Okay.
Yeah, I'll share that book. I'll email you guys, or I'll write it in the Moodle page. About that. It is somewhere here in my. I'll check. Either it is there in my bookshelves or in my office. So I'll check. Anything else? So let me stop the recording.